Okay, in this example, I'm going to talk about how we can use a frequency or a period of rotation to figure out the force required for something going through circular motion. I thought sort of the simplest example here would be the sun and the earth and how it's rotating around in this giant, I know it's not really a circle, it's kind of an ellipse, but practically we're going to treat it as a circle for the purposes of this question. And what we're going to do is we're going to figure out what force should be required to act on the Earth towards the sun to keep it in this circular motion. Keep in mind, of course, this diagram isn't anywhere near to scale or anything like that. I'm just drawing it. I don't know why. Okay, so the mass of the Earth we have is 5.98 times 10 to the 24 kilograms. And we actually have the period of rotation for this fairly easily. I didn't write it in the question because I thought I'd give you a chance to think about it. The period of rotation for the Earth around the Sun is what we call a year, 365. We go 0.25 plus that extra little bit of days because every fourth year we have to have that leap year. So this isn't really useful. Oh, and this distance between the Earth and the Sun is 1.49 times 10 to the 11 meters. And so if we think about it, if we imagine this is a giant circle, that represents the radius of our circle. Let's get this period into seconds because obviously that's what we need to use for our equations. So 24 hours per day. Hour, minute, second. So 1 hour, there's 60 minutes, and 1 minute, there's 60 seconds. So 365.25 times 24 times 60 times 60. And I get 31,557,000 seconds. 7,600 seconds in a year. Let me just do that again because I want to make sure I don't screw this up. 24 times 60 times 60. 3,155,7,600. Good. Okay. So our formula here is that the force is equal to mass times the acceleration. And if you watch the last video, I changed the acceleration from a equals v squared over r for periods to 4 pi squared r over t squared. So if you want to see how I can make that change to put that equation into period, go back and look at the last video. So get the mass times 4 pi squared r over t squared, 5.98 times 10 to the 24 kilograms. So there's nothing really special here. This is just going to be a lot of calculator work. Okay, let's see if I can get this right in the first try here. 5.98 exponent 24 times 4 times squared times 1.49 exponent 11 divided by 3,155,7,600 divided by 3,155,7,600. Oh no. And I got 3.53 times 10 to the 22 newtons. That seems huge, but it's on the order of the size of the Earth, so I think it might be right. I'm just going to punch it all in one more time. When I have big calculations like this is my little trick, is I just do them twice. And if I get the same number twice in a row, the chance that I screwed it up the same way twice in a row is pretty low. So I'll accept the number. 353 times 10 to the 22 newtons. Okay, so I got the same number twice, so that's not so bad. I'm kind of curious when I'm looking at this, if I were to use F equals ma to figure out what that actual acceleration was. So 3.53 times 10 to the 22 newtons, 5.98 times 10 to the 24 kilograms, and acceleration. I remember doing this the first time and being a little bit surprised that the acceleration works out to be as small as it does. But I guess it's a very big circle and we're going around it, even though we're going around it very fast, our actual change in direction or acceleration isn't really actually all that big. So 0.0059 meters per second squared. Yep, that's right. Okay, so we can use this formula for period to predict forces for things with uniform circular motion. And if it had been a frequency, we could have used the frequency formula instead.